Well, good morning. Thank you very much, Al, for the invitation to speak today.
Let me go ahead
I
and
oh
introduce you first.
yeah, that'd be great.
Everybody, this special is a special event for the Vertical Flight Society's eVTOL Flight Test Council. All right. And in this council, we talk about all kinds of practices for flight testing. And we have all kinds of different subjects. This is a particularly interesting and widespread subject, and VFS has graciously agreed to not only host it, but also post it later on YouTube. We think this kind of presentation will stand the test of time, and people will come back years from now to look at this. This presentation is the second part of a two-part webinar. The first session recording was with Dr. Steve Foland, and Stephen was presented about batteries. That was 2 months ago, and we want to give everybody a chance to digest it. And then here's the part two. And this is part of a paper that GAMA had published some months back. And this entire presentation that we're going to hear today is put together by Ryan Naru and Craig Smith. I don't think Craig is with us today. He had a whole lot of stuff that popped up on his calendar, but I think Ryan's got the helm. So with no further ado, the eVTOL Flight Test Council is going to hand it over to Ryan to run this presentation. We got about a full hour here to talk about energy management on batteries. So with nothing further, over to you, sir.
Thank you, Al. And I think something that the Flight Test Council will understand well and resonate with is Craig is actually in the desert doing flight tests. So he was not able to make it today, but wishing him tailwinds on the project that he's pursuing right now. Al, thank you for the introduction. I also want to thank you for the time today for this special meeting. The purpose of this paper, which is titled Managing Range and Endurance of Battery Electric Aircraft. It's developed by GAMA. It's a publicly available report, and I believe that it's been linked in the invitation document. If not, I think it'll be re-upped later. Is to begin to increase the fluency, right, that our industry professionals have on some of these key novel issues related to the design and operation of battery electric aircraft. I don't know if Steve mentioned this in our last presentation to this group. The informal kind of colloquial title for this report was always "There is no dipstick." And that really, while it's a joke, kind of cuts straight to the heart of the issue, which is there is no single measurement that you can take of a battery system, an electrochemical battery system. Let's focus maybe on lithium-ion battery systems for the purposes of today's discussion, to understand not only its current state, right, in terms of capability, but also what its future capability will be with enormous precision. And what I'm sure that Steve would have left you with, and we're going to kind of just touch on some of that again before we get into some of the other parts of today's discussion on operations, is fundamentally any one of these battery electric aircraft are going to require a performance model, right? A model that is grounded in a rigorous collection and validation of data about the performance, not only of the cells, but of the assembled cells into the full energy storage system as it is on the aircraft, right? And so there's many phases of testing, right? We're not going to go into all that today. What I want you to take away is there is going to be some dependency, right, as we experience with our EVs today, even on the road, right, of a computer that is taking many different measurements of many different variables. It could be voltage and impedance and temperatures, and taking all of that, maybe thousands of times a minute, thousands of times a second, potentially, and factoring that into a estimation of what the aircraft or the system will be capable of producing. In this case, torque output, right, on a shaft to produce power for a mission with an aircraft. And so while I can't do the full depth of that technical presentation justice today, I do encourage you either to look back on Steve's presentation, which goes into some of the underlying characteristics of an electrochemical battery energy storage system that you should better understand, why that kind of feeds into the discussion today, And feel free to reach out to Steve or any of the GAMA participants for any questions you might have. Again, this is also meant to be a primer. Like it's a 101 kind of level topic, especially as we get into the operations section. Nothing that we present here today is the only solution. As we know in aviation, it's always a trade space, right? You can sacrifice some performance on one end to get simplicity on the other, or vice versa. There will be many different operational models. There will be many different design models. And in particular, I fully anticipate that there will be many different human-machine interfaces, right? So for example, if we anticipate that the aircraft has an underlying performance model that's going to take lots of different measurements and produce an output to a human who's operating the machine, that output has to be meaningful in terms of the data that they need to complete that operation safely. That means no more than they need and no less than they need. And so how that's communicated, especially in a very dynamic system, right, which can vary based on how hard you push, right? If you're asking for a gentle set of power or a more aggressive set of power, right, that is going to factor into, are you performing above or below what was anticipated for that state, that moment in your flight plan. So let's dig in. I have about 20 slides. I'm going to try and do my best to also save some room for discussion, but at any point, feel free to throw a hand up or throw something in chat. And I think Al can help adjudicate, right? If there's any questions we should pause for. So, thank you. Great. So what you're looking at here, at least on the black line, right, is a highly simplified model. In fact, I'm going to click ahead of what the battery's power availability is going to be, right, across a particular mission. That slide that you saw ahead is a little bit more representative. But imagine that black boundary right there is either the beginning of life envelope in the solid line, which is your capability of the aircraft to produce the power that's necessary. So that's the y-axis. And the x-axis is the state of charge, right? So and we're actually moving from, in this graph, 100% state of charge on the left, because we're trying to think about it a little chronologically left to right, right? How does the mission progress? So we're going from 100% state of charge on the left to 0%, which is not really a real thing, but let's just say, and low state of charge on the right. And we have two envelopes, right? A beginning of life envelope and a derated or capability envelope. And then there's also an end of life envelope. You see that with the yellow bar here. Now, again, the proportions of these lines, the specific character and shape of the lines is not meant to be perfectly representative, right? It's just meant to be illustrative of the concepts, right, that we need to understand as we kind of move forward. And so what you can see here is, as you design an aircraft that may potentially have a VTOL profile at the end of the mission, you're going to want to be aware of when you anticipate you'll need that high power availability to complete the mission. Because as state of charge decreases, moving from left to right on the x-axis, the power capability of the energy storage system is going to decrease too. What you don't want to have happen is that you'll run into a situation where you don't have sufficient power to complete that VTOL mission. And as Steve would have spoken about in the last session, right, there's some interesting things that we can trade off at the ends of missions, particularly when it comes to reserves and maintaining safety of flight. So for example, if I'm a pilot operating this aircraft right now, on the y-axis here, we have the battery voltage. There's an energy loss from high power use, right? This is not energy we can recover. Again, left to right, state of charge, 100% on the left, 0% on the right. We're thinking about this chronologically. What is the aircraft going to be capable of? How do I communicate that information to the pilot? What does my performance model need to be able to do, right, to make sure that the pilot doesn't inadvertently get themselves into an unsafe situation? And so, again, as we've talked about, the battery has the input, right, from the pilot, which is going to be the power demand. The battery is going to be the source of that. There's measurement noise. Here's the measurements we could take: voltage, current, temperature, etc. But we also use that predictive model, and that predictive model can have all kinds of complexity underlying it. It can be, essentially the chemistry level, like micro scale complexity, some of the material science kinds of understandings of how batteries perform over various states of their health life cycle, right? Beginning of life to end of life. Or even some very simplified prediction models, right? If I'm developing, let's say, an experimental electric aircraft, I might not need the kind of complexity, right, to derive the ultimate performance that I might need. I might be willing to take some performance sacrifices, give myself some margin, still get to the outcome I need. And then a little bit of correction, boom, we get to a state estimation, right? What is my power capability? What am I going to be able to do in my mission? And so as I'm flying along, if I am anticipating either a vertical landing profile or a conventional landing profile, we can see that at this moment in time, right, the performance model would suggest that at some time in the future, right, maybe it's at a destination that I've put into my FMS, I may not have the vertical landing capability. So we would not want this mission to be planned in this way, right? So there's a lot that goes into the pre-flight and the en route segment to make sure this situation does not happen, right? So we can work backwards from our understanding that this is a possibility, right, into how do we do appropriate pre-flight planning, which is essentially what VFR reserves are all about, and en route energy management, fuel management. The interesting thing here too, though, however, is that the aircraft that you see here would be capable of a conventional landing. Low power use conventional landing, if we follow sort of this power demand graph here, right? Very, very much in the capability of the aircraft. Again, we get into some of these interesting trades of, I might have 30 minutes of endurance here, but I might not have VTOL capability. So something to keep in mind. This is not true for every aircraft. I'm not trying to make a general statement, but these are the kinds of questions that come up. And so with all that in mind, we'll leave it to the OEMs to design the systems that enable safe flight, that communicate the right information at the right time to pilots. This is the paper really speaks to the fact that this is a very significant human factors engineering problem, right? But it's also one that's being worked, and that the human factors engineering process is really the one for each specific aircraft and its concept of use to underlie how it should come out. The paper did not want to specify a particular type of indication system because, like I said, the spectrum of electric aircraft can be very, very broad. Some of them are CTOL, some of them are VTOL. We did not want to get into prescribing in this paper a particular solution. But that then brings us to the operational aspects. And so if we think about these aircraft flying missions, right, which is their purpose, right, between points, in some cases potentially producing revenue, we want to be thinking about energy management. And I think that many are becoming more and more aware of essentially, we're calling them here performance-based reserve frameworks. I would probably prefer to call them almost objective-based reserve frameworks or risk-based, right? We're trying to understand what it is that we're trying to mitigate, and then we're taking the steps with appropriate margin to mitigate those risks, those hazards. And those frameworks may not be time-based reserves. So we'll talk about that in a little bit. I think that many of us on this call are probably familiar with the Avianca crash in the early 90s, where a large transport aircraft flying into JFK actually exhausted all of its fuel and crashed in the North Shore of Long Island on a repeat approach to JFK at night. That incident or accident, excuse me, led to a establishment of an ARAC for fuel planning and management. This paper, this advisory circular, which is a draft, but the report in general, I think is a really fantastic guidepost, right, for any of these discussions. It really gets into all of the nuances of pre-flight, en route, and emergency situations that I think are, for even electric aircraft, a really useful grounding point, and it's a source of information we pulled from within this group. And so for conventionally fueled aircraft, right, the measurement of remaining fuel quantity and burn rate can typically support a reasonably straightforward estimation of remaining range and endurance. For an electric aircraft, it depends on batteries, right? We talked about that there's no single equivalent measurement. We talked about that there's no dipstick. It's a continuously computed solution. And so the information the aircraft provides must be sufficient to plan, right? So we're talking about the pre-flight, and to execute the en route, a mission with suitable contingency options, and it should support continued safe flight and landing during the emergency condition, right? So we're talking about the information systems there. Some of the basic requirements of this system will need to know when the equivalent of a minimum fuel or an emergency fuel scenario develops, such that the pilot can communicate to air traffic control to declare that emergency or to declare min fuel, and also to declare the remaining endurance to air traffic control. So this is a very typical procedure. Electric aircraft should not be upending the air traffic control system just to enter service. Right. So one of the clear starting points, right, for any one of these systems, although we tried to avoid prescriptive requirements in this paper, we really believe that you need to be able to communicate endurance. You need to be able to communicate when you're reaching critical points that require special handling and prioritization from air traffic control. For example, if you need to divert to a general aviation airport to do a roll-on landing because you have more endurance, right, to complete that mission versus a VTOL-based divert. Was there any questions that I can take at this point, or should I continue?
I'm not seeing any questions in the chat, so it looks like you're good to go.
Excellent. And we talked about the simple to complex. It looks like I kind of got a little ahead of my slides here, so I'm going to try and catch up. So let's talk about today's existing time-based reserve planning concepts. Depending on what circle you run in, right? Either these are very simple, very easy to comply with, or you could say that they're perhaps insufficient, right, to mitigate some of the particular risks that might be present in a battery electric VTOL aircraft. Why? Because the language is pretty inspecific about what you need to do when you arrive at your destination airport. It does not really speak about flying an approach procedure. It doesn't talk about being, essentially just about above the pad and then diverting. It says that you need to arrive at your destination, arrive at very, general language there, and then at normal cruise, continue for 30 minutes. Well, as we talked about before, that doesn't really manage what happens after you arrive at that destination and what capability you may want to preserve, right, after you have arrived at that destination. Similarly, it's worth noting that this margin that we factored into the time-based reserve frameworks, at least for airplanes with 30-minute reserves, dates all the way back to 1946. We did a Federal Register trace all the way back until we couldn't find editions of the Federal Register. We couldn't find editions of amendments, but the language all the way back to some of the earliest cars is essentially the same. It's one of these oldest rules on the book. But you have to think about what kind of technology, what type of mission planning and flight planning was available to the pilots, what type of weather information that kind of mandated then that 30-minute reserve. Does that same sort of framework carry forward, right, into the urban environment? What you see is with the introduction of helicopters in the mid-century, mid-20th century, some of the capabilities of helicopters, but also their differentiated missions, the differentiated weather predictability, right? Because you're sort of in a microclimate, lends itself to allowing for a shorter time-based reserve, a 20-minute reserve. And actually today in New Zealand, for air tour operations, Rotorcraft are allowed to, for missions, I think less than 15 minutes, carry the same amount of endurance as reserve to just get back to the original point of departure. So if you have an 8-minute air tour planned, you only need 8 minutes of reserves. And that actually provides a lot of flexibility and usefulness to those pilots. But it is inherently what we're about to talk about next, which is a kind of risk-based reserves mission planning framework. And so what is a performance?
I just wanted to interrupt and inject the importance of what you're about to talk about. This is absolute key to success for a lot of these urban air mobility aircraft. So this is a big foot stomper. Sorry to interrupt. I just couldn't.
No, it's a great point, Al. Right? I mean, we're kind of getting to some of the meat and potatoes here. I mean, really, the intent of the paper was general education about all of the sort of energy management nooks and crannies, right, of electric aircraft. And this is one of them. If you look back, though, to like 2020, 2019, many of these powered lift were thinking they were going to be airplanes. And so many of them had factored in 30-minute reserve, like a post destination endurance, thinking about, right, complying with those airplane operational rules. We'll see where the SFAR turns out. EASA has also moved forward with actually a non-time-based reserve for these VTOL capable aircraft. This is not a special carve out. Like, what I want to talk to you about today is actually with performance-based rules and performance-based range and endurance management, not a special carve out for electric aircraft. I completely believe that if a rotorcraft operator today wanted to move forward with an exemption to give themselves additional flexibility or capability by trading some of the 20-minute endurance, right, based on their fuel-based aircraft for, you know, maybe a little bit of extra payload, a little bit of extra performance, you could file an exemption for a performance-based reserve construct, I think, for that operation. I think it would make a lot of sense. There's no reason why an electric aircraft needs this, right? But we do, I think, advocate for the fact that this covers some of the particular risks that today's endurance rules do not. But anyway, let's jump into it. So what is a performance-based rule? We hear about this all the time in airworthiness. We're trying to bring this concept forward across aviation rulemaking. A prescriptive rule are regulatory requirements that dictate specific processes, technologies, or practices that must be followed to achieve a particular safety objective. And a performance-based rule is one that sets out the desired safety outcome, or the performance level, but leaves the means of achieving those outcomes, those safety outcomes, to the discretion of the regulated entity. And so a performance-based rule prioritizes explicit definition of the desired safety outcome rather than how to do it, right? How to achieve it. Like, so for example, if we're talking about reserve requirements, rather than discussing how to do it, which is thou shalt carry 30 minutes, thou shalt carry 20 minutes, right, depending on the type of aircraft you're operating, instead it might outline a set of risks that you must show as an operator, that in your mission planning and en route energy management schemes, you are mitigating. This, as you can see, right, the time-based prescriptive requirement is actually quite attractive. Performance-based rules are not always better, right? Prescriptive rules make compliance pretty straightforward, but performance-based rules may offer you that trade, right, in complexity for performance, right, complexity for flexibility. And so some of the risks that you may want to explicitly want to mitigate could be risks of adverse weather, right? Today, actually, the time-based endurance reserve does say accounting for weather and winds aloft, right? That is a little bit of part of it, but you can carry that forward. Any sort of delays, air traffic delays, diversions, go around, instrumentation uncertainty, performance degradation, right? Did I end up flying the mission with a landing gear that wouldn't retract, you know, and I wasn't maybe informed of that? Maybe my indication system wasn't functioning right, and I have a performance degradation. So I need to be able to track en route is something happening that's going to affect my ability to think and understand, am I going to be able to complete that mission as I expected to or not? And so what you get to is, again, these kinds of factors I think would underlie a performance-based reserve concept. You need to be aware of your performance capability. For an electric VTOL, that means both energy and power capability. You need to be able to cover all phases of flight. You need to be able to cover emergency conditions. That's that off nominal factor column. Ideally, it's adaptive, right? So it identifies your alternates, right, as part of the pre-flight planning. It allows for you to account for cruise and landing power availability needs. And again, it's flexible, right? If you have a really strong understanding of your weather in your region of operation and the likelihood that a go is going to switch to no go on your landing in flight, you might be able to then make an argument for less or more margin on what you're going to carry in terms of, you know, a post capability reserve. A little bit on the mission hazard assessment that's kind of discussed in the paper, right? You have the mission profile, the capability limits, weather, off nominal contingencies. Landing access is kind of interesting. Are you going to a site that's like a heliport? may have a discrete number of places you can put down, or is your intended operating site a airport, a general aviation airport, where there's tons of ramp space, you have the ability to do a roll-on landing at the location itself, right? That may, again, factor into, for this mission, a specific estimation of risk that you have to mitigate, and then the specific amount of margin that you may want to carry, for example, to get to an alternate, to be able to have the capability to safely land, to continue that mission and safely land. So we talk now, again, going back to the electrochemical side of this, right? There's going to be probably two capability thresholds that you want to factor into your mission planning. The first is a critical capability reserve or margin. I'm going to call them margins instead of reserves to minimize kind of the confusion with the time-based concepts. But a critical capability margin is one where you're accounting for some kind of failure, a performance augmenting failure or a power augmenting failure when you're arriving or getting close to the site, right? So am I going to have a battery failure? If I go from 6 batteries to 5 batteries, that will affect the total power availability I have to complete that mission, right? So that envelope that we talked about in that very first graph is going to move in to the left, right? And so it's going to get closer to what you need. You can plan a mission, right? So that way you can account for your worst case power augmenting failure and still arrive and complete the mission at that site. Alternatively, and that framework is a little bit like PC1, Cat A, right? You're going to be able to do whatever you need to do throughout that entire segment. The other option, right, would be planning a mission around a nominal capability, right? So you're saying from some landing decision point where this power availability becomes critical, and this may be just a 30-second window at the end of flight, I'm going to accept the risk, right, that I may that a failure might affect my ability to safely land, to continue flight and safely land. With Rotorcraft today, right, we don't treat HV envelopes as explicit limitations in all cases. It really depends on customer requirements and the operator's tolerance of risk. But an HV envelope is really something that's printed into a Rotorcraft flight manual for the purposes of that risk trade. Am I willing to fly through that HV envelope for, a couple of seconds on an approach and departure, where if I have some sort of critical failure, I may not be able to auto rotate down, right? HEMS operators operate this way all the time, where they may need to come in very steep, very slow. If they have a failure, that's not going to be a good day. So we do accept risk in vertical flight. And so these are 2 points you could notionally plan a mission around, and 2 sets of margin you can think about incorporating in that mission planning. In addition, so there's an energy indication assessment, right? How much energy derating, how much margin do I might have in the performance software itself, right? That's going to indicate capability to the pilot. Am I telling them the absolute truth or the truth with like a little bit of hidden margin in there, right? Do I do that because I don't have perfect capability to assess the performance of the battery, and so I want to put that margin in to protect myself as well? And then this is a very interesting concept, and one that I think doesn't get enough attention, which is the en route segment of energy management in this performance-based reserve framework. So today, we look at the VFR reserve as you shall not begin a flight unless you have this capability at your intended destination. Here, what you're looking at is something that is accounting for the fact that how hard I drive my battery, or if there's some sort of unindicated failure that affects performance, I may be ahead of where I expected to be in terms of my battery state of charge for a particular point en route, or I might be behind, and I might be significantly behind. You may be able to set those limits for yourself, where being a little bit behind is acceptable because you gave yourself enough margin at the arrival destination that you feel like all risks are able to be accounted for. But if you're very behind, let's say you had a very taxing takeoff for some reason, right? Maybe you needed to stay thrust-borne for much longer for some reason, and that really now, based on where you expected to be in the mission, you're far behind on state of charge. Now you're looking at a divert. You're not looking to complete that mission. You're looking to essentially go somewhere else. All of that should be pre-planned. You would have pre-planned decision points, right, based on these sort of these energy check-ins, right, these power availability check-in points along the mission. All right. So the next slide, folding all this together, and I know this is a very complex eye chart. I really encourage you to go to the report to try and digest all this. But this is essentially saying, if you go back to that original chart, how do we factor in those margins? This purple line here is a off-nominal power augmenting failure, right? I'm going to need to be at an earlier, like essentially a higher state of charge in order to have the power availability, right, which is that black line, in order to complete a VTOL landing, which may require more power because, for example, I may have less batteries to supply the required power. I might be C-rate limited or otherwise on those batteries. I might have thermal limits on my EPUs. I might, for example, if I have 8 propellers, be down to 6, right? Well, what does that do? That drives your disk loading up. That increases the power required to produce the same amount of thrust. So for all these reasons, there's a lot of power augmenting failures you may want to consider, right? And then decide, what state of charge do I need to have to arrive? Like, what is the absolute minimum? And then what is the acceptable margin that I need to have at that arrival point to give myself the flexibility I need to complete that mission safely with my essentially tolerance of risk? Maybe I'm willing to tolerate more risk. Maybe I'm willing to say, I want to accept that nominal capability at my landing point. That might move my state of charge that I'm allowed to arrive at to the right. I may be now also accepting that power augmenting failure is not one that I'm planning around, right? I'm accepting kind of a proportional risk to some of the kinds of hazards that exist when it comes to like one engine inoperative or worse, right, in a rotorcraft. So again, not advocating that this is the way to go, just recognizing that these are decision points that need to be made by an operator or a regulator. And then beyond that, right, what's not shown here, because it would have been way too complex of a chart, is there a point where I'm accepting, a CTOL landing is an acceptable final choice, right, in terms of how I'm landing. The thing that's not really shown here is, and it's hard to conceptualize, so you have to kind of think about it in real time. You have to close your eyes and imagine yourself in that situation, is where is that landing decision point? And when is that last point, right, where I've committed myself to landing at a particular, let's say, VTOL site? Up until that landing decision point, you may not have gone all the way to the top of this power demand graph. You may be somewhere here in semi-thrust-borne flight at a lower power demand. And so the only time that you're exposed to this very high power envelope is in the total thrust-borne, the last phases. And so you're reducing the risk exposure window significantly because of how much time you may be experiencing in that thrust-borne phase. Not, again, advocating for any particular solution, but these are things that you may want to factor in, because if I can, at that landing decision point, say, failure experienced, right, going to alternate, you may be able to then, let's say, proceed at cruise power to a CTOL landing site and still be able to continue safe flight and land. So there's choices that you have. Either you want to tolerate that failure all the way to touchdown, or you want to kind of factor in some sort of landing decision point and give yourself a different choice in terms of how you want to land. As you can see, this is a very complicated topic. It takes a lot of thought, and it can really significantly impact the capability of the aircraft on a particular mission. Just another kind of way of looking at this, again, sort of in the battery voltage graph terms. I'm not going to spend too much time on it here, but again, you can see a critical capability reserve, a nominal capability reserve, and then some of that energy derating in the nonlinear end of the battery, right? We probably don't want to ever expose ourselves to an area that's very difficult to have a performance model with high accuracy, unless we're accepting that in that phase we'll always kind of be in a final cruise glide segment. So again, complexity. In this graph, what we're starting to introduce is those concepts of the check-in point. So I'm going to just rewind, right? Am I behind or am I ahead? Do I need to divert? And so what you're looking at here is when I might have an off-nominal event, when might I be behind? Where does that place me in terms of relative position to those critical capability margins or critical capability reserve, however you want to say it. Very complex, hard to read graph. Not going to suggest that you do that live here, but this, I think, makes it a little bit more illustrative. And actually, this is derived from ETOPS philosophies. If you go back to that 1990s report from the Avianca incident, right, you'll actually see kind of a macro scale version of this graph and this illustration for, let's say, a transatlantic flight that may have a limited number of diverts to Greenland, Iceland, et cetera, to Nova Scotia, to the Azores. And what we're doing is we're microsizing that concept, right? You're looking at a mission, let's say, from Irvine to Santa Monica, and along the way, you have planned check-in points, right, where you'll make a decision. At this point, I'm either, or at least up until this point, I'm going back to KFUL. Beyond this point, it makes more sense for me to go to KMET or KEMT. So you're trying to essentially then build this power capability graph relative to your total capability to make sure that you have enough margin, enough endurance, right, to make those diverts. Now, early in the mission, you're going to have lots of margin, right? As you get closer towards your final destination, right, you get into some of those, again, interesting decision points. For Santa Monica, right, you now may be able, so long as there's still a runway, factor in that CTOL capability at end of mission, right? Maybe you go in for a thrust-borne landing that didn't, you hit your mission decision point, now you're going around and you're approaching with a CTOL capability, you still have that performance. These are the kinds of concepts we're trying to introduce to this industry, to familiarize them with, to think about, how do I do pre-flight? How do I do mission planning? How do I do this to make sure that I'm achieving safe outcomes? And this is essentially that in practice. I actually just illustrated it with my mouse, but here you go. You see a graph and this is a notional, right, way of communicating it to a pilot, right? What you see maybe is a endurance ring, a range ring for the aircraft. I think that's for the off-nominal event, right? So still having critical VTOL performance within that ring. Lots of things that could affect that too, right? In terms of indirectness, altitude, terrain, et cetera. So this is notional, right? This is just to start planting the seed. And similarly, you might have this ring, which is I've arrived at my destination. How much, let's say, VTOL capability do I have after that? How much CTOL capability do I have after I arrive at my destination? Where are my choices? Where are my options? This may not be something that you present in flight, probably won't be something you present in flight, but again, it's just to try and plant concepts of how this might go, how you might have very dynamic capability throughout the flight, how you might want to flight plan. All right, we're at the summary. I can catch my breath. I'll take your questions as best I can. But between the two presentations, these two special presentations that Al was so graciously able to offer the GAMA working group who developed this paper, we've covered a number of really high level things. So that includes understanding high voltage energy storage systems, their characteristics, how that then informs the integrated system and its capabilities. We talked about the fundamental importance of performance models and how that then plays into the human factors engineering that will go into your indication systems. These performance models are inevitable, whether or not you are building probably a light aircraft or a very complex VTOL. Using a voltage, a straight measurement from a battery is always going to be a pretty poor way, if not an unsafe way, to understand current and future capability of the aircraft to end a mission. Now, in a CTOL environment, that might be acceptable, but yeah, we think that there's probably some sort of simplifying performance model that goes into the indication system that supports pilot decision making. And then we just talked about this concept, which has been circulating for the last few years, on what is the alternative to a time-based, an endurance-based reserve requirement. Are there other options that may be more complex from a compliance standpoint, but provide more flexibility in terms of mission planning, total capability of the aircraft, minimization of the total use, let's say, or allocation for a battery in pre-flight? Does that give you more operational flexibility throughout the day, right? Does that open up new markets, new missions, more people, right, to the promise of advanced air mobility? And I think that the one thing I just want to absolutely double click on is this is a concept that I think would be available to conventional aircraft today. I think it's a concept that could be promoted and accepted for CTOL electric aircraft as well, right? If I was looking at building a CTOL electric trainer, right? I know I've heard a few companies who have presented at conferences that say, if I'm going to build an aircraft that has a meaningful training mission and I need the 30-minute reserve after that time, right? I'm looking at an aircraft that has a very challenging endurance requirement from a design perspective. But if I also look at precedent, for example, with the International Aerobatic Association, and I might have misnamed that, excuse me if I did, there is a blanket exemption for all members to not need to carry 30 minutes of endurance fuel on board a acrobatic aircraft that's staying in a an acrobatic training or display execution box at a single airport. And why is that? It's the same reasons that we just talked about from a performance-based, risk-based, objective-based reserve concept. You know exactly what the weather is going to be in that area. You know exactly what your divert point is, right? Where you're going to land. All of these risks are being mitigated inherently by the mission. And so how is that altogether so different if I'm flying at, say, a multi-copter like VTOL, and I may just be hopping over a river or a bay, right? I know that the New Jersey side of that micro weather environment is probably not all too different from the Manhattan side. And so if I have a very performance limited electric VTOL, am I enhancing safety by requiring that multi-copter to have 20 minutes of endurance? Or is it too much? Is it unnecessary? Am I able to essentially explicitly name what the risks are and make sure that to my regulator, I have a scheme that appropriately takes those risks into account, both in the pre-flight, in the en route, and in the emergency condition case? And I think that, sorry to keep rambling, but we just saw the final rule for SMS be published for Part 135 operators and also for Part 21. But, I think that now that we have these frameworks to both assess and track, right, particular risks, and I think that there's a lot of opportunity to explore these concepts here in the US today. So anyway, I'm done with my prepared remarks. Happy to take questions, and I'm very grateful for the time presenting today.
Okay. Yeah, thank you so much, Ryan. I'm sure we're going to fill the next 15 to 20 minutes with questions and comments and so forth. And so if you would raise your hand. I see Andre. We got Andre already raising a hand. We're going to try to get to everybody. Let me start off with a couple of big picture statements here to sort of transition. So this, just to be clear, our council is the Electric and VTOL Aircraft Flight Test Council. Our concern is being the best flight testers we can. And in the process of being good flight testers, we have to understand the limits of our aircraft, right? In terms of endurance, how far can I go? How many data points can I get on a flight? So a lot of what Ryan is talking about here applies to us, because we have to actually fly the thing. So we're going to be the first ones to understand these limits from our perspective. But professional flight testers are very disciplined, and we brief things very thoroughly, and it's a bit of a different environment. But we're going to be the first ones checking this out. But the big picture here, the big discussion, and I don't want to put words in the mouth of any of the regulators, so I'll let the regulators speak for themselves. But what you can see, and again, supporting what Ryan had to say, the 30-minute rule is, comes back from historical. Fuel gauges are only so accurate, and there's only so much training, and pilots at this kind of flying, and the 30-minute reserve for VFR worked. And it'd be different reserve for IFR and so forth. It was all based on a average or a conservative estimate. And what we're talking about here is, hey, the FAA cares about being safe. And of course, all the regulators care about being safe. If an operator can show them, here's how I'm going to be safe, and here's how I do the math, then each operator can make a case. But notice I use the word operator as opposed to airworthiness certification. All right. If I go to certify an aircraft and the rule says I have to have 30 minutes of reserve, okay, I'll use that number. If the rule says I need 45 minutes of reserve, okay, I use that number. I don't make the rules. I just show that the aircraft complies. What we're talking about here is what is necessary to show compliance. Okay. And in this case, each operator can do it a little differently. And this is where it gets really interesting. And it's not laid out yet. So if I'm going to have an aircraft that goes from point A to point B, back and forth, just as Ryan mentioned, I'm just hopping the river, okay, and it's a very contained environment, it's a 10-minute flight, you know the weather, you can, with that sharp pencil, you can ask for less. But if I'm going to go far ranging, what's different? So I think each operator can make a case. And what we're trying to work up here is the language for doing that. And what are the rules? And if you're going to go to the regulators, how do you make the case? What has to be on your checklist? And that's a big part of this conversation that's going to spring forth from that. So with that opening comment, let me first go to Andre. Andre, what do you got?
So thank you for the presentation. And just to resonate with what you said, Al and Brian, I think you're bang on the parallel that you make to ETOPS. That's great. That's great to see this concept. And the side that I would offer is that it's different than a Part 23 aircraft operation then, because if you're operating ETOPS, let's look at the ETOP side, you're a Part 25 type operator and you're specifically approved for that type of operation. So we got to bring these concepts together, right? For a small craft that is a Part 23 like that we see here, and an operation that is much more thought of. But bang on. Thank you.
Andre, the point is super well taken. I absolutely do not believe that the first rollout of a scheme like this would be for a Part 91 private operator. There's absolutely no resources from a regulator's perspective to oversee individuals, planning and capability management and their conformance right to that actual operation. That would be really, really hard.
Yeah.
There might be ways with technology that an OEM provides, right, to that one day could support that and monitor that, but that is probably not the first step. And so to your point, right, if we're talking about ETOPS as like just a way of thinking and getting into the head of how do we look at a operator's specific approvals and risk management systems, yeah, I totally think it's going to be 135 like operations or the equivalent, right, as the first places for approvals.
Thank you.
Yeah. Mr. O'Gorman.
Hey, Al, thanks for the floor. Morning, Ryan. I love the presentation. Your power graph and the expenditure there is exactly the concern that we have when we're starting to talk about, yeah, that one's 44 is perfect. 41 as well, sure.
Yeah, I'll go to
I don't know
44,
if you were part of any of the presentations where we've had some discussions on the turbulence index. The one piece that I felt that was missing from the discussion today, I love the ETOPS parallel, but ETOPS, you're always landing at a runway with the kind of known environment, whereas the operating conditions for these aircraft, we're often talking about urban canyons, right? So the concept of even hopping across the river, like you said, yeah, the overall weather is known, but the conditions on that particular vertiport might be very different than what you're expecting. So what we've been discussing in this group before is the development of a turbulence index, which really is an indication of how much power you're going to need to land at a particular site. So depending on the turbulence of various sites and the readings that the turbulence index is giving you, it would inform the last phase of the flight here to tell you whether you could successfully land at that particular deviation point, or if you have to go to another alternate.
William, that's a great point, right? And what we're talking about here is, I think, vertical margin or variability or unknowns, right, on some of these power demand graphs, right? So if you have a site that may potentially have high architectural turbulence, right, that would require more power from the aircraft, let's say, to complete the thrust-borne landing, right, then you may have a clean day, which is probably like with low state, and then let's say a high turbulence index, maybe you're higher up on what your expected demand might be. So I think that's a fair point. And that's really what I'm trying to encourage here, is for people to think about this and bring their own expertise right into the idea space. This is just a first step. This is the first time we've really communicated things like this outside of some small operator to regulator discussions, right? And so
to run with that,
thank you. Yeah.
Our initial discussions on the turbulence index were more based on the performance capability of the aircraft itself. So it was more of a go, no-go concept, because the turbulence existing at the landing site may be above the capability of your vehicle to withstand.
Yeah, without question.
This
and I think that
inform even more tactically whether you have the power reserve to now use those sites. So yeah, quite an interesting relationship.
Totally.
If you could go back to slide 44, I'm going to extend that conversation, because you nailed that, William. So what we need for the pilot is the human-machine interface to make good decisions. All right. And something like this, you're hopping along, and all along the way, you need to know what's possible. So in addition to the turbulence index, you're going to need some sort of real-time feedback. Especially, I'm glad you used the Southern California example, because there's fog, and something could be happening, outside of turbulence that could keep you out of a VFR landing. And so you probably need some real-time influence into the system. If we're going to shorten the endurance requirements, if you want to make a case saying I don't need 30 minutes, then you have to back that up with saying, because I'm constantly monitoring my facilities and I'm constantly doing this, and that's why I can do it. You have to build that case. So in addition to the turbulence index, it would be vertiport operations. If a baby, my favorite example is a baby carriage goes across the vertiport. Okay, you got to divert. You can't land, or something like that. It gets fouled. So all that has to be part of the real-time calculation. Now, as far as presenting the pilot the information, this has been a recurring topic in our subcommittee on electric flight testing, and how do you give the pilot that information so you can make good decisions. And one of the things we've been talking about is SOAP, state of available performance. Somehow all these different parameters that are associated with the power that you can get out of the aircraft, and the voltage and state of health and all this somehow comes into a calculation that tells the pilot, much like you've displayed right here on this chart, here is your bubble where you can land. You have this space. And so if it's there you go, there's the bubble. If that's constantly presented to the pilot saying, in a normal landing, here's how big your bubble is. If you need to make a precautionary landing, it could be a different bubble. Or if you want to make a wing landing, then you can just point to, a display to the pilot saying, hey, this airport is in the green zone, this airport's in the green zone, and you constantly feed that to the pilot. So that's one of the things we're talking about to make it operationally viable. Again, you have to have the sharp pencils. To me, the question, Ryan, is how far along is industry now at understanding all the parameters would have to go into that SOAP calculation so we can make a SOAP bubble?
Yeah, and I think that's going to depend on particular operators who understand their aircraft and understand their missions. And I don't want to speak for anyone writ large, right? An industry-wide blanket statement probably wouldn't reflect, right, where certain folks are at, what they're trying to achieve. But I can tell you that I've been getting caught to this issue, right, for the last 5 years, going all the way back to Uber Elevate. And right, I mean, it's all about how do we deliver that promise of safe, efficient, affordable access to air mobility, and to do it with the technology that we have available today, right? So I believe that there's a path forward. I think that the safety promotion of what the Flight Test Council is doing here today, what GAMA is doing to put out a paper like this to increase kind of the baseline for dialogue, right, in terms of the technical, level, right, of that dialogue, I think is really important, because now we're maybe able to go to that next step of specifics. If you're an operator, if you're a regulator, right, you've already understood some of the concepts that we're presenting here, and you can go into implementation.
And I would like to add the kudos to Joby for letting you do this and letting this is why Joby's out in front on so much, because you guys are sharing this information and you're helping. As you progress, you Joby, will there be some sort of a Joby standard that you release and say, here's how we're showing, here's how we're doing the math, and everybody else needs to meet the hurdle we're setting? Or is that sort of thing proprietary and you do it on your own, you negotiate separately with the regulators?
I'm gonna turn the question around a little bit and first say this is definitely not Joby, right? This is a fantastic group of really motivated and safety-minded people in GAMA, in the trades, who are developing work like this. This work is really a lot of effort from Beta, right? Especially on that first half. Dr. Foland did a ton of work here to make sure that information was available to folks. Similarly, Craig Smith from Overair, who wasn't able to be with us today, did a ton of work on this section, right? And I'm really presenting on his behalf. So, I appreciate that folks look at Joby as kind of a leader here in this space, but I want to acknowledge that all of industry is pulling their weight. All of us are safety minded. All of us are trying to get the best performance too out of our vehicles. So, I think that I'll kind of keep it there. I think that the kinds of things that you're seeing out of this, you might see more specifics. You're going to see follow-on papers. I think that this is just version 1, right, of this document. There's either going to be subordinate documents, follow-ons, revisions, right, as people become more experienced and want to provide more specific examples.
This is great. Let's do one more question. We got Doug Schmidt. Doug.
Thanks. Hey, can you guys hear me?
Sound good.
Okay, good. Hey, I know we're running out of time. Real quick question. Forgive my naivete with the subject matter. I'm here to learn about it. When, in your experience, battery temperature, how crucial is that to these calculations for range and endurance? And what I'm getting at is, for my very basic understanding of the technology, you're using the battery temperature will fluctuate both from use and from the environmental factors of climbing into higher altitudes. How impactful is that on these calculations, and how much does that complicate these like real-time calculations, getting at the subject matter of the human factors aspect of giving the pilot a prediction? And again, the main concern here is, how much more difficult does that make it to show the pilot what's going to happen when you don't know how much power output they're going to demand from the battery? How much?
I couldn't have asked for a better question to end the presentation on my favorite phrase, which is there is no dipstick, right? And so as a pilot, I'm not going to be looking at temperature information either from the pack level or individual cell levels to try and, go to my knee board, look at my charts and try and figure out, do I have 10 minutes left or 12 minutes or 14? But that information is crucial, and it's crucial in not only the real-time aspect, but also what did you anticipate when you were planning the flight? I think a lot of these OEMs are going to be developing planning tools that factor in how they expect, right, with certain power demands and environmental conditions, the battery temperatures to fluctuate, and therefore what their performance will be that point 10 minutes in the future when they may be performing a particular maneuver or procedure. And that is really what I think goes into the human factors engineering as well, right? We believe, at least I believe, that all of these variables, which you can measure many times a second, feed into that performance model. That performance model is underpinned by lots and lots and lots of cell, module, and integrated pack testing. The cell labs that I think all the leading manufacturers have to run relevant mission cases, but also abuse mission cases at various conditions to characterize these batteries and develop and inform these models is key, right? And just as we certify the charts that go into a Rotorcraft flight manual today that would allow you to do these performance calculations, the certification of the digital model, right? Essentially a digital RFM, right? Allows for these. What is the safety objective? The safety objective is to be able to complete the flight safely, right? In normal and emergency conditions. Whether that's in a book on your knee pad or whether that's in a digital system, you just need that information to complete the flight safely.
It's going to have to be, it's too complicated to boil it down to a dipstick number. That's the bottom line.
Thank you, Al, for slowing me down. And thank you, everyone, for going over time. Al, I'll leave it to you to close.
All right. Thank you, sir. So once again, this was a special meeting of the Electric and VTOL Aircraft Flight Test Council. And we'll go back to our regular schedule. We meet every 2 weeks. And if you're interested, the contact information will be on the YouTube link. And those of you that are already council members, you know where we meet and so forth. Once again, I haven't introduced myself. I'm Al Lawless. I'm the chairman of this council. And I'll be here every couple of weeks, and we got lots going on. So if anybody is interested in the flight test side of electric and Rotorcraft, let me know. Thank you very much, and we'll talk to you at the next webinar.
Hey, Al.
Sir.